I propose that we get started by just going around and you introduce yourself. And I also would like to know, what is your why? So what is the big why you're interested in QuDits? So what's inspiring you to look into QuDits?
Yeah, I'm Martin. I have a background initially in photonics, then via quantum mechanics I went into trapped ions, and now, as you heard, I'm responsible for building QuDits, quantum computers with trapped ions. As for why we should do this, I think it's just wasteful not to, because we have all these nice quantum systems, be that atoms, superconductors, photons, whatever. They're all high-dimensional. We have very good control over them, so we might as well use those particular spaces that we're getting there. And I mean, I find it interesting that in going from classical computing to quantum computing, a lot has changed, but the one thing that sticks is this binary computing, which really doesn't look like the way to go for quantum systems. So yeah, I think we should get rid of that and just try to look at our problems and look at our computing system and match them in the best possible way, right? Be that QuDits, bosons, whatever we have.
Susanne.
Okay, so I'm Susanne Yelin. My background is theoretical quantum optics, and I started to go into more serious kind of quantum information, algorithms and theory a couple of years ago. My access is actually via quantum machine learning and now via quantum chemistry. And this quantum chemistry calculation also was the reason why I basically more or less accidentally fell into this kind of thinking about both QuDits and multi-qubits, because that just basically comes out automatically if one tries to do hardware optimized applications, and then basically it gets back to what Martin just said. It's just much more efficient. Yeah. And of course, from a theoretical point of view, it's much more interesting.
Yes.
Because you have suddenly a lot more possibilities.
Right. Okay, yeah, thank you.
Okay, my name's Barry Sanders. Actually, like Susanne, I started in quantum optics, theoretical quantum optics. You said serious quantum information, but I do non-serious quantum information. That's my objective. And then I've been doing quantum computing. It's funny, the field is said to start 1994. That's when Shor's error correction paper came out in quantum algorithms. And I was actually doing quantum computing even in the late 80s. But I can't prove it because every paper got rejected, because quantum computing was science fiction then. Might still be science fiction. Okay, why do I do QuDits is the question.
Yes, exactly.
And so I'm going to tell you the truth. First time I ever told the truth on this.
Okay.
It's not that QuDits I care about, but I kind of like, actually, I think that my brain is physics, but my heart is math. So I really like the abstracting of things. So what happens when we do qubits or we do bits in a computer, and actually I worked for a while on multi-valued logic at one point, but I kind of like to separate the algebraic structure of computing from the representation, right? You don't have to do it with bits. Classically, you can imagine DITs, not very practical. There's work like the BSS machine, if you look at it, Bloom-Shub-Smale machine, which said, what if you could make a computer where every entry was a real number instead of a bit? You can ask about quantum mechanics, you can ask about nonlinear quantum mechanics. And so for me, the real fun is saying, what can I say about computing that's purely algebraic without the representation? What conclusions can I draw about computing, complexity, computability, and all that? And then, what are legitimate and illegitimate representations to plug in? So my involvement with QuDits, which goes back over 20 years, my first paper on QuDits goes back 22 years, I think, was really a matter of playing around with these ideas, saying, why do I need to work with qubits? Can I abstract it? And pulling out the beauty of it. So of course, as was said, both Martin and Susanne said about the efficiency, to me this is a strategy of squeezing juice. So if I want to squeeze juice out of an orange, and I do it with my hand, I get some juice. But if I use a squeezer, I get more juice out of the orange. And so to me, QuDits, on a practical level, are like getting a squeezer for juice. I get more out of it. But on a purely theoretical level, it's interesting because QuDits, whereas qubits, the Pauli matrices satisfy a Clifford algebra, they don't for QuDits. And so what exactly I can do computationally, what I can't, how is the Solovay-Kitaev theorem affected, what goes on with error correction, benchmarking, all these kinds of things becomes really interesting from some mathematical level, teasing out what's representation dependent, what isn't. So that's my answer.
Thank you.
Yeah, so my name is Ashok Ajoy from Berkeley, and I'm actually, my primary background is in magnetic resonance, so NMR and EPR, and then quantum sensing is a natural, I think, modern manifestation of magnetic resonance. So actually, in NMR, which is the study of nuclei, more than spin-half nuclei occur very commonly in the periodic table. Actually, most of the nuclei are more than spin-half. Like common ones are nitrogen-14. Dominant isotope of nitrogen is nitrogen-14, spin-1, oxygen-17 is spin-1, etc. And so as far as quantum sensing is concerned, most of the time we're trying to sense very small things or very weak signals. And these multi-level systems that are natural in QuDits give a natural way to be able to combat noise. I think that's where a lot of the community has focused their attention, which I think is really exciting, because if you have a multi-level system and all the levels move in a particular direction, and then you can find a way to suppress noise, because that won't be sort of common mode rejected, if you like. I feel there is the other opportunity for quantum sensing with QuDits is the fact that often you can do things at very relaxed conditions. For example, at zero magnetic field, if you use a spin and you use spin half, then both the levels are degenerated at zero magnetic field. But if you have a spin 1 or spin greater than half system, you automatically have some splittings that you can exploit. I feel the field itself has not moved too much into QuDits, although it's very widely used in NMR. Spin 1 NMR is a very commonly used technique, and it has wide implications.
So my name is Crystal Senko, and I have been studying atomic physics experiments for many, many years now. And the reason I have gotten into QuDits is similar to Martin. It's really about not leaving resources on the table. So qubits for me are very precious resources. It's very difficult for us to build up very large systems. And in the tradition of atomic physics, what we've seen for many decades before I started working in the field is that the general trend is you get very good control over the very simplest systems possible, then you build up your control over the complexity, and this always unlocks new things that you can do with your experiments. So I see QuDits as sort of a continuation of this trend of saying, as we've been discussing, we have these very complicated systems, we've learned how to get very good results reducing them down to 2 levels, but now we have the tool set to try to expand that and try to understand what we can do, what different problems we can tackle with them, and that's sort of my underlying motivation.
Mm-hmm. Yeah, great. Thank you. I have 2 follow-up questions. So the first one is about hunches. Yeah. So because we see this big potential, like we all see this big potential in the QuDits, but in terms of very concrete examples, like where do we see the biggest promise? And like I know for a fact that Martin and Susanne, you have kind of walked it with your feet, basically, those are things that we're doing now, but maybe you can both answer, like where do you see, in terms of the very concrete application, where you see, that the QuDit really gives you a tangible advantage, like basically now. And maybe, if you like, maybe we have a wild hunch for the far future where basically we should explore, like areas where we should explore where QuDits could unfold the biggest advantage or promise, or where we really want to head in which systems. I don't know who wants to go first.
Yeah, I mean, there are a couple of interesting angles one can take, right? I mean, one can start from like a fundamental perspective. There are different entanglement structures in QuDits that we don't have in qubits, right? Also things like contextuality, they appear then in three-dimensional systems but not in two-dimensional systems. So in a sense, the qubit is kind of the odd one out, right? That's what originally got me interested in this when I was still working in photonics. But then, in terms of computing and applications, I think there are a few obvious candidates, like things we're already doing, the things we heard at the workshop, right? If you have a quantum simulation problem that is naturally formulated with something like a gauge field, some discrete infinite dimensional thing, you trunk it somewhere, it's kind of obvious that you should be doing this with a qubit. Things like, which we just heard, the phase estimation, for example, right? It's also something where, like, you want to estimate this phase, you discretize it in some ways. It's also kind of obvious that you can do this naturally in whatever ways you want. Yeah, and then we just have to see. And I think what we probably have to do is look at the computer scientists a little bit, because we, at least on the experimental side, we're thinking a lot in terms of circuits. And once you think about a circuit, I think it's very too late. You need to go a step back and abstract this a bit and think about what is the function that you want to implement, right? The problem you want to solve. And then you compile it down to whatever your number is and you can see what works best.
Maybe you limit yourself when you set the quantum.
Yeah, exactly. With the bosons, fermions, and all the resources we have.
Maybe you solve it in some measurement-based elements.
Well, I mean, obviously, I'm working on quantum chemistry. Quantum chemistry has naturally various hierarchies of levels that we want to simulate that are more than two. Spins are more than two. Vibrational levels are more than two. Rotational level, you get the idea. But to be honest, if I step back a little bit, I have since a long time been starting to look into ways how to go beyond the circuit model. So in that sense, it's similar to what Martin just said. And QDIT is one very obvious direction. Another direction is what we heard today, is that we include bosonic and fermionic statistics. And honestly, a third that goes along the same way, along the same lines, is to also include actual, truly continuous variables into that. And I don't mean continuous variables as a harmonic oscillator, but continuous as continuous. And finally, I'm also dreaming about how to use all this structure to actually improve the communication between the quantum computer in a wider sense and the real world. Because if we speak, we normally speak classic. But right now, the translation between classical and quantum is very inefficient. And so my hope is that we can kind of get rid of some of the barriers, and I think QDITs and all of the other things will help a lot with that.
Yes, that Barry looks like it wants to add something.
Okay, no, I mean, if you ever ask, I always have an opinion on everything. So I was just thinking, I was talking, you mentioned the talk with qubits and oscillators, continuous variables, Susanne. And I think, Eleanor, you're back there, and I had a conversation with her yesterday. So, and as I said before, I get excited by the abstract. And so it turns out, as I was mentioning to you, there's a supersymmetric analogy. So if actually, you know from quantum optics, the Jaynes-Cummings model, and then if you pick your coupling strength right, you could just write a superoperator, A plus sigma plus, A dagger plus sigma plus. And so what I was thinking, when you asked what I was thinking, is I was just thinking how beautiful, because in the back of my mind, related to your talk, that's why actually I didn't ask you, you asked me why I didn't ask you a question, because I was thinking too much. And so, but then the idea of doing supersymmetric quantum computing really intrigues me. So what can I get out of quantum computing with supersymmetry that I wouldn't get otherwise, and how to break it? So that's what was in my mind. Totally irrelevant to what you asked, but just spicing things up.
Oh yes, as you say, spicing things up. So I have a question, but where I thought specifically about Crystal and you, actually.
Crystal and who?
because if we want to, if we want to compare, for instance, the computational power, yeah, and someone has a QuDits-based quantum computer, and someone has a qubit-based quantum computer, and like I'm not sure we have the right framework really to compare, because like you brought this up in your talk, right? Like we have a single number for when you do your gate and like 25 levels, but there's, especially if we start to talk about entangling gates, there's so much more entanglement, and there's so many more places like what should we compare? We should not compare like one highly entangled, high-dimensional gate to just a CNOT to qubits, right? So how do we appropriately compare the computational power and complexity, and also related to that, if we want to compare the errors, so maybe thresholds can be higher, there's more space and the other errors, but there are also so many more things that can happen.
I can say to start. Okay, I'll just say something at the beginning, not to displace you, but just so. I mean, first of all, when you benchmark or anything, ultimately it's related to a task. Nobody cares what the fidelity of a gate is. In the end, you just care, can the machine do the job or not? And so, with respect to a task, the QuDits, you can be more forgiving of QuDits. You know that with qubits, qubit gates are better, but you have fewer things, fewer components. A worse performance on a QuDit machine can actually be good. So in a sense, trying to compare, if you try to be fair, and you say, well, is my QuDit gate as good? You might lose sight of the fact that you need fewer QuDits. But I want to go back to a point Martin raised, which is, the first thing we want to do with QuDits is do things that we can't do without, like, what can we do that qubits don't suffice? So you mentioned the contextuality as an example. My favorite, and I was talking to Richard Cleve, I don't think he's here at the moment, but he's been in and out of the session, and Richard wrote a paper with John Watrous, who's also here in Waterloo, and others, and it was a paper called How to Share a Quantum Secret, published in 1999 in Physical Review Letters. And that one, it becomes a special case of quantum error correction, and you can do it with qubits, but not qubits. And so, to me, like if we focus only on saying, are qubits better than qubits, we're not thinking right. It's really, what can we do with qubits or beyond that won't work? Like Ashok mentioned the spin 1 case. There could be things in sensing where you need spin 1, you need 3 levels to be able to do it. And then there's one, and Martin, I don't know if you know, you're in Austria, and Anton Zeilinger is in Austria, so I know there's a non-zero overlap. And then, there was the stuff with the coin tossing. Do you know this? So in Seilinger's group, they did an experiment where they did the coin tossing, and then it turns out that, bit commitment. Mm-hmm. Bit commitment. And the bit commitment needed a qubit. So I think that was one of the early examples. So, and then there's the Perez and Beckman-Pasquinucci work on quantum cryptography from around the year 2000. And that one showed that the rate of tolerance to an eavesdropper is much better for qubits than qubits. So I think the way we should be doing this is saying, what are the cases where a qubit is a game changer, not is the qubit better at doing what qubits do? So that's my comment. Over to you.
I mostly agree with some of that, or almost all of that, but maybe not quite the last piece, because I do think it's relevant to compare what can the QuDits do that the qubits can also do, but because we're still in this NISQ era where we have these very limited resources. But back to Christine's question, I think the first thing that occurs to me when you ask this is, forget about comparing qubits and QuDits for a second. Do we have widely accepted metrics for comparing qubit-based quantum computers? I mean, we have some, but everybody has their favorite metric, and it's the metric that shows that their machine is the best one in the world, right? This is just the state of the field. And so I think that it's a ways from having clear metrics and figures of merit that allow us to directly compare these processors, other than, as Barry says, how efficiently or effectively can they accomplish the jobs that we care about. But I would say that we are going to want, I think, to do some computer architectural analyses on these systems. This is something you're starting to see with the qubit world, that people are, with classical computer architecture backgrounds are making analyses that if you have this different class of problems and these different ways of entangling qubits, moving them around, et cetera, which architectures are best suited for which problems. And I think we're going to see some of that coming out with the qubit and QDIT comparisons as well. And that's one of the reasons that in my work we're focused in part on assessing how these errors, what they are in the lab and how they scale so that eventually those can be fed into these more broad comparisons.
Yes. And so very quickly mentioned also like there's a whole advantage on like also quantum communication, because so far we focused on computing, quantum simulation, and of course this is a whole area in itself where QDITs are really important. And not sensing, and Ashok is our sensing expert here. And can you explain or outline just a little bit more where you see like the newest, freshest possibilities where the field of quantum sensing can open up now that basically multi-level systems can help?
So the answer has many parts. So one thing is I already mentioned, if you have multiple levels, you can almost internally do some sort of error correction of classical noise and be able to sense things better. Often in quantum sensing, you're trying to see some level shift in a very sensitive way. But if two levels were to shift, then you know that you can detect this shift with higher precision, because you can remove noise that is some sort of common mode between them. So it's a classic case, and that's used widely in NV centers, for example. But nowadays, with the advent of molecular quantum sensors, especially with these lanthanide elements, there are multiple levels. They're often more than 3, and sometimes, for example, gadolinium has like 7 levels, and there you can use multiple levels to help in sensing better.
And maybe a real-world application. I mean, it doesn't have to be today, but basically, this is an interesting sensing application which, in the real world, could do this for us.
Yeah, so maybe before that, I'll say that already, though, from a very practical point of view, the spin 1 things is coming back a little bit to NMR and MRI is very widely used. And I think that's a practical example that's currently present. So I'll give you 2 examples.
Yes.
One is detection of N14. It's by a thing called nuclear quadrupole resonance, or NQR. And basically turns out that you can do NMR without a magnet, because this N14 spin is spin 1, and it has the equivalent of a 0 field splitting. And so it's very widely used, for example, or rather it's purported to be used in airports for detection of explosives, contraband, etc., all of which have nitrogen, and you can detect nitrogen just by passing it through an NQR machine. The NQR detectors are less sensitive, but it remains a frontier direction to be able to increase sensitivity of NQR. Another very interesting example is deuterium imaging. So as you might know, MRI is the detection of water in the body. We are all 80% water. And so when you go into an MRI machine, you're just mostly seeing structure, which is where water is, what are the different types of water. But the body can tolerate a large amount of HDO rather than H2O, because it's heavy water, but as far as all chemical reactions are concerned, it's like water. And so you can feed someone, or you make them drink deuterated water, heavy water, or you can inject it, for example, to your heart, and it can tolerate a lot of heavy water. And so frontier direction is trying to do things like angiography with MRI, where you're not imaging water, but you're actually imaging deuterium. And you could do that because if you did image deuterium, you won't get any background. So you don't see, so you'd use the MRI image of water to see the structure of the heart, and then you would do deuterium imaging to see where the water is going in the heart and be able to do angiography in real time. So that's a very interesting frontier direction. Deuterium is spin 1, so it turns out to be slightly more complicated to do, but and so I can talk more about why it's complicated, but that's a practical application with enormous significance, because it would be equivalent to a radioactive tracer with no radioactivity, and the body can tolerate a lot of it.
Yes. Yeah, that's an exciting example. Right, and okay, so like we fleshed out or glimpsed at all the opportunities. Sure.
I'm going to ask you, but you can hear me, but they can't. Okay. Yeah, so I'll ask you a question. Can you hear me? So when you say that, like the NMR, there's sequences of pulses, very famous ones, long sequences. And then if you're doing it with deuterated water and spin 1, I imagine that it would be like these NMR sequences but QTRIT operators, qubit. Is that what happens?
Yeah. So exactly. So so the main complication is twofold. One, the gyromagnetic ratio of deuterium is slightly lower than proton, and so the signal is lower. So you need to find a way to boost the signal, and so there are some complications there. And the second disadvantage is so you can imagine that you've got this level that's automatically set by something in the spin, but it's pointing in some direction, and you have a magnetic field which may or may not point in the same direction. So often you have in all these spin 1 systems an orientation dependence based on how the spin is actually pointing with respect to an imposed magnetic field. This can work to your advantage because in things like oxygen NMR, or you can, in glasses, etc., it can tell you structural information, but it becomes a little bit more complicated to handle. But it's a question for quantum control, basically. But it's been worked on significantly.
Yeah, later on we also have a section of questions from the audience. Didn't know we have also a section of questions from the panel. So I have one more question. So problems, yeah? So what do you think are the biggest problems? Oh, Barry.
I don't always want to jump ahead, but I do have one that keeps me up at night. So it's kind of therapeutic to share it, maybe.
Yeah.
So,
There's
okay,
always an open ear here.
and I made clear that, everybody else here, I think, really cares about practical, and I don't, so it's not a practical problem. But I'll tell you this way, that, we write a Pauli-Schrödinger equation to describe how the qubits evolve, and then what Ashok's describing could be, a spin 1 system. We know how to do it. But then there's the whole field of relativity. In relativity, we have the Dirac equation, and so we have, if you think about the 4-component spinner, Dirac spinner, it's got electron spin up and down and positron spin up and down. And then the Feynman interpretation says that antimatter can be regarded under CPT transformations as matter going backwards in time. And so the positron is an anti-electron. Well, if the electron serves as a qubit, then the positron serves as an anti-qubit. And the anti-qubit's going backwards in time. So what keeps me up at night is, and that's a Q-quart. But it's a Q-quart by a different dynamic. So what keeps me up at night is knowing that if I make quantum computing relativistic, I wind up turning qubits to Q-quarts, and some of them are going backwards in time, and can I take advantage of time travel to change the complexity of solving problems? So that's what I think about at night. And now we can hear our answers.
Okay, I'm intrigued. So, Ashok, do you want to share what's bothering you?
No, I think it's more an opportunity rather than something. So I think it's an opportunity to be exploited. But I think just like any experimental platform with QuDits, I think the biggest challenge is to control all these levels. That becomes a rather challenging quantum control problem. I guess in Crystal's case, you need lasers. And even in spin qubits, you need to address every transition separately. And based on where the transitions are, it's a lot of overhead on control that you have to bring to bear. I think that's a challenge. And specifically with respect to spins are concerned, you have this strong orientation dependence, which is another challenge. So these are 2 experimental challenges.
Okay, I have to say what is left to say is a little bit anticlimactic. Fortunately, time travel doesn't keep me up at night because that's over already, right? I think that the very obvious one is the control. For me, what keeps me up at night is also the extra opportunity. So if we have qubits and universal quantum computers, there are some very clear ways how you translate your problem into the circuits. Once you have QuDits, there is no unique translation anymore. So we have to actually kind of find an optimal translation. And this optimal translation is so far, everybody who works with QuDits at all does that classically. But what do we do when this classical optimization of how to write that into a circuit with QuDits becomes NP-Hoyt?
Yeah, I guess along those lines, maybe one thing I'm thinking is we're missing a lot of the infrastructure that we have for qubits, right? We don't really understand entanglement beyond qubits. We don't quite know what are the good gates that we should develop, that we should use. We don't know what are the kind of good forms of entanglement that we should have. How do we compile these circuits, like you say? How do we compile these things to make it efficient? I think on that side there is a lot that still needs to be done.
Yeah, I agree with that, and I think from a university researcher perspective, I think that's a great thing because you can jump in on pretty much any problem with QuDits and say, okay, there's some low-hanging fruit here that we can study, that we can learn something new about. I think where maybe I'm concerned is I start to see these companies and these governments trying to build very large-scale quantum computers. They're often way in science fiction land talking about what are we going to do with millions of qubits, and like, okay, we don't have millions of qubits. But they are thinking hard about a lot of the conceptual infrastructure and the classical compilation and all sorts of issues related to translating this lofty goal of solving some interesting problem down to brass tacks or, quantum hardware, as the case may be. And all of that infrastructure, more or less, in industry is qubit-based. And so when I'm working on my little lab experiments, we're having lots of fun with it, but I do wonder sometimes, are any of the people who work on scaling these to extremely large systems, are we ever going to be able to adopt the QuDits, or is it just going to be such a heavy lift to reinvent all of that infrastructure that we're going to find that it's just sort of a toy academic problem?
So do we have any question from the audience? Yeah, I see one back there.
I asked this also because it's kind of related to what you're already talking about. Is some of you are sort of theorists and some of you are experimentalists, and I'm sort of curious, what is it, from the context of QuDits specifically, do the theorists think that they would like to either know more of or maybe see the work in the experimental side? And from the experimentalists, is there something that you think would be interesting, in theoretical work? I'm just curious, obviously, to see from both sides if there's anything that's you think is missing from the other direction.
Well, if somebody would like to tell me what can actually be done with a 25-level QDIT, that would be super cool. So come at us with some ideas.
Yeah, I agree. Actually, I think at least from the narrow perspective of quantum sensing, I don't think there's been clear roadmap on what could one gain by using multiple levels and in what context. And I think it's a well-posed theoretical problem that could be interesting.
Can I talk as somebody who is a theorist but comes to the qubits from the practical side? So for me, coming in here, QDIT is a spin d-half system. So what we have heard is mostly not exactly that, but it's a system where every level, and Ashok said that before already, where every level is separately controlled. And I would like to know from the experimentalists, or would wish me from the experimentalists to go more to this clean kind of high spin system, and from the theorists, which of the two types of QDITs are actually more useful at the end?
I agree with that. Yeah, connecting to this, right? I think we just need to talk a bit more and at a bit of higher level, right? I want to know from you, how does the problem look like that you want to solve before you write down the circuit, right? Typically, we talk about, yeah, this is the circuit that needs to be implemented on the hardware, right? But we need to go a step back. We understand what is the problem, what are the capabilities that we have, what are the capabilities that we need, and how can we meet in the middle, right?
Okay, and for me, as a theorist and working with experimentalists, which I do, QDIT based, I mentioned in my talk about working with Andrea Morello's group on the SpinCat. Jack and I are talking about things with her photonic QDITs and various other things on the go. I'm kind of looking for the game changers. So what I said, like not making things better, but what can we do experimentally with existing capabilities that would be game changers? So for me, working on a high spin nucleus and realizing a cat state on that, to me, is an interesting result. Theoretically, it should work, but getting the experiment to work is non-trivial. And I mentioned earlier about the some of the quantum cryptography stuff. There's the how to share a quantum secret. There's the bit commitment. And so in my head, I've got a list of QDIT experiments I would like to see happen. And so, for me, I would like very much to see, and if necessary, even to help, see those game changers happen.
Is there another question from the audience? No? Oh, yeah, yes, he's there. Okay.
I would like to know more about this concept mentioned earlier about having a good canonical way to write down circuits that represent the processes that you care about with QDIT systems. So what would you consider to be, what are some of the criteria that you see as relevant when deciding on the right language or the right, let's just say, gate set for writing down these processes?
Well, that was part of the last talk, wasn't it? The whole ZX, is the person here? Yeah, I mean, that was the point there, to write down one way to be able to write a QDIT circuit. Is that what you're asking?
Yes, but what would make, let's say we do have several different graphical calculi. From your point of view, or even from an experimentalist point of view, what makes a language particularly good? What makes it easy to use?
So somebody else can answer.
So I think there immediately to mind come for me two things. The one is what can be done with the particular experimental system that I have. And the other one is what language is good to do things like, for example, complexity proofs or so, for which we have to have something very standardized. And often these two are coming really from the very opposite ends of the spectrum. So these are two aspects that I find very important.
Martin would probably say, is it even clear that you have to make a gate-based circuit? Yeah, right. Any more questions? Oh, okay. I don't know. I think you were first.
It seems to me that in the qubit land, there is the part of promise of scalability is the existence of a huge amount of work in like quantum error correction and fault tolerance. And so there are works with QDITs on also quantum error correction, but it's not, it seems not nearly as well developed, right? So it's, is it a hard problem to solve? And do you think that will prevent the QDITs from achieving, could that prevent QDITs from achieving kind of advantage or anything like that, if maybe that's like impossible to do? Or do you think that's like just a matter of time before we can do that?
How hard it is depends on how smart somebody is. So Einstein found things easy, other people didn't. But, it's interesting. We had the talk, remember 2 times 3 is 0? Joseph Ebers's talk, right? And, why is he dealing with prime dimension? So if you want to do benchmarking error correction and you say that QDITs have prime dimension, it's easier. But then if you get to the point where you're dealing with fields of, well, not fields, but you have composite number dimension, it gets harder. So, I mean, to me, that's the fun thing, is that we can do everything with QuDits that we do with qubits. Probably there's, asymptotically, you know, if you care about exponentials and polynomials, there's no change, but there's a little bit better performance. But mathematically, it's not as trivial. So you have to put more brain cycles to work to get fewer results. Most people don't like that. You know, if you use qubits and you can get the answers easier, it's better. But if you want to, you know, challenge your thinking and do things that have marginal gain, QuDits is a great field.
But if you're trying to persuade like industry to pursue that, then that's not like really good.
No, that's the squeezing more juice out of it. Yeah.
Well, if I could pick up on that, I think there is more work to be done on developing quantum error correction and fault tolerance for QuDits, for sure. But I think one of the patterns that we've seen in qubit land over and over is that as soon as you have experimental capabilities to implement something, then all of a sudden there's a whole set of theorists who mostly focus on what they consider very practical problems who are all of a sudden interested in these systems because now the experimentalists have said it can be done. That's by no means everybody, but I think that sort of community tends to be where a lot of these theoretical advances come from. And so now that we are starting to see all of these experiments demonstrate QuDit operations in the lab and say, this is a thing, we know how to do it, tell us what to do with it. This is, I think, likely to start bringing in a lot more collaborations. And you start to see that already with two of our panelists here, where we have a QuDit processor in Innsbruck and an expert in nuclear physics who are all of a sudden, you know, teaming up to solve some really interesting problems that nobody could figure out before. My hope is that quantum error correction will go the same way.
I got really excited the moment when I realized that the ion trapper could actually run a real QuDit circuit, and like a full-fledged QuDit algorithm. That was the moment when I was already happy. Yeah.
That was perfect because my question was also about quantum error correction. Yeah, my question is like, what needs to be happen from both experimental and theoretical sides to realize QuDit quantum error correction experiments? So what are the main barriers in your opinion? For example, I think in Martin's talk you mentioned that you have a linear in the QuDit dimension overhead in the amount of operations, but I think because you are getting a quadratic increase in the size of the qubit space, then that's a pretty good trade-off to make. It's just that the current system sizes are kind of on the verge of being big enough to run small experiments.
Do you think we have we solved the problem with qubits? Is there error correct? Like, part of it is we can't even correct qubits yet. So, but if we get to a point where we're doing good error correction, universal error correction, we'll have entangling and all that. So it's kind of like, what are the list of requirements to do real quantum error correction? Now, there are terms that get bandied about nowadays. They call it quantum error correction, but it's not textbook quantum error correction. So what you're saying, it's kind of like, if we can solve the problems with qubits, then the qubits will fall into place. QuDits will fall into place.
Maybe a clarification of the question is like, what kind of barriers or timescale you think we could get break even? That's a specific thing that you could see, but then, like example,
For us, we first need to figure out what the thresholds are, right? I mean, and Barry pointed it out in his talk, right? A lot of the early literature on error correction was actually done for QuDits, and then people realized, okay, there are no QuDits in experiments, so we do only qubit stuff. And then the past 20 years, we're kind of making the error correction practical and looking at what are the real errors that are happening in the experiments and how can we deal with these things. How can we deal with things that are not correctable errors and so on. That needs to be done for QuDits as well, right? At least for prime dimensional QuDits. But there is some work to be done on the theory side before we even know what the target is.
Very, very briefly, I have absolutely no idea about the time scale of QuDit error correction. But the thing is, we have heard in several talks, and we see that also in our simulations, that QDIT-based approaches often give errors that are so much lower than QBit approaches that we don't need to think about error correction yet, because we are already, without error correction, we are already ahead. And so I think why people will probably start thinking about that very soon, just because people are curious, how can we expand all of these ideas of whatever, LDPC codes to QDITs, whatever. There is, I think, right now, no hard necessity compared to qubit approaches.
Can I do a quick follow-up on that? Do you think there's a limit in like how many qubits that would be true for? Yeah, right. Because when like qubits, you could argue like if you have like 1 qubit, you know, or like 2 qubits, you don't need error correction. So like, yeah.
I don't understand the question.
How small does your error need to be? How often can you let your circuit run, etc., right? I mean, this is hard to put an absolute value on this, right?
Just how much longer are we able to like get away with the errors, with the lower errors? I was just wondering.
Okay, I get it. I'm going to tell you why we can't answer the question. So it's interesting. So in quantum computing, we have the fault tolerance quantum error correction threshold theorem, if you know this, right? And so that just says there exists some limit with respect to the diamond norm that if we pass it, then we get scalability, right? This is what we target. But it's an existential, not a constructive proof. So we know it exists, we don't know what it is. Then if you go back and you look, like Manny Knill's work in Nature way back does it, he says, okay, well, let's start constructing codes. So if you want to figure out where we're at, then you start saying, okay, I'll try this code, and then you put a bound on what that threshold is. The challenge we have, too, is that we don't even have good codes. So the way I think about it is we know the thresholds exist, but even as a theorist, for me to say, okay, if you give me a QDIT, make it a prime dimension to make it easier, and then I want to do it, then I have to construct the coding theory to replicate like what Manny Knill pioneered to be able to then get an estimate of what it would be. So even trying to, like back in the old days, 25 years ago or so, we had like these 5-9 proofs, right? You had to get 5-9 fidelity or something or in order to get scalability. And right now we're kind of stuck on that method. Does that make sense? Yeah, so yeah, I think we have to have a map where we construct proper codes to be able to then start to simulate under reasonable error models to guess where it's going to be. Joseph kind of touched on that in his benchmarking talk.
Ella wanted to ask something, no?
Kind of just on this error correction and direction, I was just wondering if an intermediary step, and maybe this is just we missed someone talking about it, but has everyone thought a lot about erasure, QDITs, and for example, in ion traps, like what would they be like?
I'm not sure I understood the question. What?
So I was wondering if between now and full error correction on the QDITs, whether some form of erasure mechanism, so...
Right, error mitigation, something like that. Yes, I mean, you should do as much error mitigation as you can before you get into error correction, right? Because the overheads are typically much smaller. There are certainly things you can do, and a lot of the things that we have for qubits also generalized to QDITs in terms of mitigation, like dynamic decoupling and these sort of things, right? And we heard some of that also at the workshop. And that can go a long way for certain kind of errors. But it's certainly now the time that we should start developing error correction tools, or we need that soon, I hope.
We have time for that. I was about to say last question, but I think Hubert and you we have 3 people who want to ask. Like Hubert. Okay, then.
So I'm curious if you think there's any tools missing from classical DITs, because I feel like when I speak to my friends in like computer science, engineering, like they're very much, classically, it's binary that we solved that decades ago. And I mean, more the more engineer people, the theorists still have done some. I'm curious if there are still some holes in the classical world optics that we may also need to collaborate with more classical people to build that up so that we can then lean on for QuDits.
Well, maybe, yeah, I can, because I'm senior in age, so I kind of remember the history of these things. But it was, so first of all, when your friends who are saying that kind of thing, classical world, there's a whole IEEE group, MVL, multi-valued logic. So these things exist. And there was a period back in the 1970s, I think Isaki got a Nobel Prize for the transistor, and then the diode. Then there was the resonant tunneling diode by Tsunosaki. And so this, for a while, was seen to promise a multi-valued logic. And then all these, there's a conference every year, there's journals dedicated to it, and it's all classical. How do you design computers that would be multi-valued logic? And to prove that it will take over eventually, if you ever watch Star Trek, that TV series, and they talk about their computer capacity, they talk in things like gigaquads. So it's clear in the 24th century that they're using base 4 and not base 2. So it's inevitable. But the thing is that, it's right, I know, it's a product of, it was a power of prime, well, if 2 is prime. So yeah, so there are open questions, and there are people who think about it, but it's a very small number. But like coding theory and all that really does relate in the classical world that we need to see. And then there's also a reversible computing group. And so some of the leaders in the field, like Charlie Bennett and others, came out of reversible computing. And then you can start saying, well, classically, what happens if I marry the multi-valued logic community in the IEEE with the reversible computing group in the IEEE? And a lot of questions come up. And then, like we saw in the ZX calculus, remember the Toffoli-Hadamard part? Yeah, so that one, that kind of, if you do Toffoli's without Hadamars, you're into the reversible computing direction. So when you talk about QuDits with Toffoli's without the Hadamars, this is kind of Toffoli's universal and reversible computing. So my short point is, in fact, a lot of the challenges exist in the classical setting. We shouldn't get our minds too cluttered about the more complicated part about doing quantum. And your friends, you need friends from the 24th century. You're stuck in the 21st. That's the problem.
Maybe I could also briefly say that the whole conceit of quantum computing is that there are some problems that we think will be much more efficient on quantum computers than on classical ones. And assuming that that's the case, it's not clear to me that you really need to be making direct comparisons or to be drawing from classical computing because, for example, adding 2 numbers is an extremely trivial thing to do in the classical world. That you wouldn't want to try doing this on most quantum computers because why would you want to waste those resources when you could just do this somewhere else? So I think that the problem domains are probably going to be different even when we go to the QuDits.
Mm-hmm. By Zabit.
Oh yeah, I just have a question which bothers me. I don't know how to go about it. And this is about entanglement. We say it's a strong correlation, quantum correlation with no classical analog. At the same time, we say the quantum system in D dimension, there is a D+1 classical analog. And when we talk about tunneling, if you go to imaginary time, then you flip the potential and you can do classical dynamics. Is there any way we can keep this line of thoughts, finding an extra dimension that will turn the entanglement into something that will be classical?
So I think if I understand it, probably you're bothered by you're trying to recover local realism. Is that the idea? Is it philosophical?
Is there any classical analog to entanglement? Can we, because we said this is no classical analog for the entanglement, is there any way to add extra dimension and see if it's, like in tunneling, if I go to imaginary time, then I can do classical mechanics and recover the tunneling.
Yeah, so you're kind of saying, so if you think of a Bell inequality with 2 qubits, and they're entangled, and you're saying, what if these qubits are secretly qubits? So I guess what you're saying is, if you could, is there a way that you know that 2-level systems are really 3-level, use the 3rd level of each classically, local realistically, and then convince somebody that you're violating a Bell inequality, but it's classical in higher dimension. Is that what you're asking?
Yeah, I'm asking, yeah, adding one extra dimension.
So I'll just say something here. So I don't, Norbert Lukenhaus is not here at the moment, but he opened the meeting.
Yeah, not yet. Not
So
at the
it comes up, this comes up in quantum cryptography, and then
Yeah, and Tony Asin would have to say something.
yeah, but they're not here, so
Yeah.
I'll say something. Yeah, so then in Norbert Lukenhaus's approach, and maybe he'll be at dinner or something, but Norbert developed this model of squashing, right? So then the question comes up that if there's a higher dimension, but if it's spam, right? If your state preparation and measurement are done in a lower dimension, and then you start to feed in, you have other dimensions in between, can that be a risk? So this came up, like if you do quantum key distribution and you do an Eckert version, which has the entanglement, could that third or higher level be there? Like, can the adversary know that your two-level systems are really three-level systems? And so Norbert's work on squashing and others, they say, well, if the measurement is restricted to two levels, they pull back the math through it and then show there's no loophole. So that's my take on it, is that if you build in the state preparation and measurement, then the higher dimensions can't do it. But I'm not the expert, but Norbert would have something to say, like you say, Antonia seen.
Yes, yes. Okay, so like we close this. I have an absolute last question. It's like a bit more of a personal question. So I would love to know from each of you which is your favorite number. Do you want to start?
Let's pick 17.
42.
Aleph 1. Aleph 1? Yeah, Aleph naught is the countable infinity, and Aleph 1 is the first uncountable infinity.
Yes.
So I have 3, I, pi, and E.
I can't say I ever selected a favorite number.
To get to know you a bit better.
I feel too personal.
So what's your favorite number then?
Well, I have actually 2. My 2 favorite numbers are 73.
Somebody who does QuDits.
Okay, so on that note, so again, big thank you to you for being my panelists, and also big thank you to you for being our audience. And yeah, I guess we are all looking forward to dinner. But before we can make any dinner plans, we shall assemble together for a photo, and we shall all follow Dave to the photo spot. Okay, and a round of applause for our panelists.